All right, strap yourselves in because we are going deep into quantum computing today.
Sounds fun.
You guys sent in a mountain of articles and videos
wow.
all about Microsoft's big announcement, this Majorana 1 chip.
I saw that.
And let me tell you, they are really hyping this thing up.
Yeah, they're saying it's like a transistor moment for quantum computing.
Yeah, transistor moment. Pretty big claim.
Yeah.
And so to get to the bottom of it,
Okay.
maybe we should start with like the basics.
Yeah.
What actually makes quantum computing so different from the computers that we're using every single day?
It all boils down to how information is processed.
Okay.
So like your laptop, my phone, they use bits.
Right.
Which could be either a 0 or a 1.
Right. Civil.
But quantum computers use qubits.
Ah, yes, qubits.
And that's where things get interesting.
Okay.
Because a qubit can be a 0, a 1, or a both at the same time.
Whoa, both at the same time.
Yeah, it's because of these funky laws of quantum mechanics.
I think I read about this. It's called superposition, right?
You got it. Superposition.
Yeah.
So these qubits are essentially doing this balancing act, holding both 0 and 1 possibilities, like simultaneously.
Okay, but even if one qubit is doing that, how does that actually make the whole computer more powerful?
Yeah, good question.
It still just sounds like one qubit.
Right, so that's where entanglement comes in.
Oh.
So entanglement is this crazy phenomenon
where
two qubits become linked, even if they're physically separated. So it's like they have this like...
secret handshake.
Yeah, secret handshake, where whatever happens to one qubit instantly affects the other one.
Wow.
So now imagine a whole bunch of these entangled qubits all doing their superposition dance at the same time.
Okay.
So they're not just individual units anymore. They're working together, exploring tons of possibilities. At the same time, that's where the power comes from.
So it's kind of like they're a team of super-powered calculators,
Yeah, that's a good way to put it.
Working in perfect sync.
Yeah.
But hasn't it been, like, really hard to actually make this work?
Yeah, it's incredibly difficult.
Like, for decades.
Like, building a quantum computer.
Yeah.
It's almost like trying to assemble a puzzle while you're on a roller coaster.
Oh, wow. That's a good one.
Right, because qubits are incredibly fragile.
Yeah.
And they're susceptible to any kind of disturbance. Scientists call this...
Right, I've heard of that.
So even the slightest, like, vibration or temperature change can throw them off.
Oh, wow.
And then that leads to errors in calculations.
So it's like you're trying to build a computer, but the building blocks are super sensitive?
Yeah, exactly.
Okay, well, how do you actually build a computer if that's the case?
Right, well, that's the million-dollar question.
Literally.
Literally, right.
Yeah.
And that's where Microsoft says they've made a breakthrough.
Okay.
With this Majorana 1 chip and their topological qubits.
Topological qubits, all right?
So they're using a whole new type of material. It's called a topoconductor.
A toconductor?
And get this, it's considered a new state of matter.
What? So they're not just like tweaking old technology, they went back to the drawing board?
Completely new.
All right, so what exactly is a toconductor then?
Yeah, so a topoconductor is...
And how does that create these more stable qubits?
Okay, so a topoconductor, it's a material with unique properties that allow for the creation and control of these things called Majorana particles.
Oh, Majorana particles. I've heard of those.
Yeah, they were actually first theorized back in the 1930s.
Wow, that's a long time ago.
Yeah, and even physicists think they're pretty bizarre.
Okay.
Because they're their own antiparticles.
Wait, what does that even mean?
So that means, under the right circumstances, they could essentially annihilate themselves.
So they're building a computer out of particles that can just disappear?
Well, it's not quite that simple.
Okay.
But it's this property of being their own antiparticle that makes them so valuable. For quantum computing, so by braiding these Majorana particles together within the topoconductor, Microsoft believes they can create a type of qubit that's intrinsically protected from that noise. That's what you were talking about earlier.
So they basically wove a shield around the qubit to protect it from all the external chaos.
You got it.
But how does that, like, translate into a computer that can actually do something useful?
Well, they're betting that this topological protection is going to allow them to scale up to 1 million qubits.
1 million qubits?
On a single chip.
Okay.
And not just any chip, a chip that could potentially fit in the palm of your hand.
Wow, so you're saying this tiny chip
Yep.
could unlock all that potential we've heard about with quantum computers?
That's exactly what they're saying.
All right, so why is 1 million qubits so important?
Well, it's widely believed that 1 million qubits is like the threshold.
For what?
For actually tackling truly impactful problems.
Okay.
Things that are just impossible. For even the most powerful supercomputers today.
That's crazy.
Yeah, and Microsoft is saying that they can achieve this level of complexity on a scale that no one else has even come close to.
So this little chip could be the key to unlocking things like designing new materials, discovering life-saving drugs, all this stuff. It sounds like science fiction.
Yeah, it does.
But Microsoft's not the only one trying to do this, are they?
No, definitely not.
There's other people in this quantum race.
Yeah, there's a few other notable contenders.
Like who?
So we got Google with their Willow chip.
Oh, yeah, I read about that.
Which boasts a much lower qubit count.
Okay.
It's still making some waves.
Yeah.
And then you also have IBM, who set their sights on building large-scale quantum computers by 2033 using a different approach.
So with all these different approaches, how does Microsoft's bet stack up against all the competition?
So Microsoft's argument is that their approach isn't just about qubit count. They think that their topological qubits are fundamentally more stable and reliable and easier to scale than these other types.
So they could potentially jump ahead of everyone else.
That's what they're claiming.
Okay, that's a big claim. So they have this groundbreaking new material.
Right.
They have this chip architecture, and they have a big vision for the future.
Exactly.
But are they really on the verge of a breakthrough?
Well, that's what we're here to find out.
Okay.
So Microsoft claims that they can achieve commercial viability within years, not decades.
Wow, so that soon.
Yeah, they're even comparing it to Moore's Law.
Oh, wow.
Suggesting we're about to see like a similar exponential growth.
So we're going to see this quantum computing power increase rapidly.
Yeah, that's their claim.
All right, well, even with all this optimism,
I
can't help but wonder about the real challenges that they're going to face trying to actually pull this off.
Sure.
Building something atom by atom.
Right.
Surely that can't be easy.
Yeah, you hit on a crucial point.
Yeah.
Manufacturing on that scale with that level of precision.
Yeah.
It's a feat of engineering unlike anything we've seen before.
Right.
And that's just one piece of the puzzle.
Yeah, exactly.
You know, even if we like set aside the engineering marvels for a second, just the implications of what Microsoft's attempting are, like truly staggering.
Really?
Yeah, they're not just talking about building a faster computer.
Right.
They're talking about building a tool that could fundamentally change our understanding of the universe.
Wow. Okay, so they're trying to build a lens to look into the quantum realm.
Basically, yeah.
Wow, that's amazing.
So imagine, like, being able to simulate the behavior of molecules with perfect accuracy.
Wow.
Or, like, model complex biological systems down to the atomic level.
That would change so much.
Right. It could revolutionize fields like medicine, material science, even our understanding of consciousness itself.
Okay, I'm starting to see why they're so excited.
Yeah.
But with all this talk about revolutionizing everything, shouldn't we also be thinking about the downsides?
Oh, for sure.
What happens if this tech falls into the wrong hands?
Yeah, that's a crucial question, and one that needs to be, like, carefully considered.
Right.
So, like, one of the most immediate concerns is the potential impact on cybersecurity. You know, quantum computers could crack the encryption algorithms that we rely on today to secure, like, online communications, financial transactions, even our critical infrastructure.
So all of our passwords, bank accounts, government secrets.
Potential vulnerable.
That's a little scary.
Yeah, it's definitely something we need to be prepared for.
Okay.
So governments and security experts are already working on developing quantum-resistant encryption methods.
Okay. That's good, at least.
Yeah, but it's a constant race to stay ahead of the curve.
It feels like we're entering this new era of, like, technological warfare where the battleground is not a physical space, but the digital world.
Yeah, it's a sobering thought.
Yeah.
But it really highlights the importance of responsible development and international collaboration in this field.
Yeah, for sure.
Yeah, we need to make sure that quantum computing is used for good.
Right, of course.
Not for, like, malicious purposes.
So it sounds like this technology could be both incredibly beneficial and potentially dangerous.
For sure.
What are some other areas where we might see a big impact?
Oh, that's a great question.
I remember they mentioned applications like breaking down microplastics.
Right.
Designing self-healing materials.
Yeah, that's right.
It's like something out of a movie.
Yeah, it does sound like science fiction, but those are just a couple of examples of the transformative potential.
Yeah.
So imagine a world where we can design materials with specific properties from the atomic level up.
Okay.
Creating things that are stronger, lighter, and more sustainable.
Wow.
Right.
It's almost like having a molecular 3D printer.
Exactly.
Where you can craft materials with incredible precision and control.
Exactly. And the potential applications extend way beyond just material science.
Like what else?
So quantum computing could revolutionize drug discovery.
Okay.
Allowing us to, simulate the interactions between molecules.
Okay.
And design personalized medicine.
Wow.
Tailored to an individual's genetic makeup.
Now we're talking about some serious life-changing applications.
Yeah.
Let's shift gears for a sec.
Okay.
Back to the technical side of things.
Yeah.
You mentioned that Microsoft's approach relies on these Majorana particles, right? Have they actually proven that these particles exist?
Yeah, that's where things get really interesting. So, Majorana fermions have been a theoretical concept for decades.
Okay.
It's only recently that scientists have been able to even create and observe them in a lab setting.
Wow, so Microsoft is building their whole strategy on a particle we barely understand.
That's right. It's definitely a high-risk, high-reward endeavor.
Yeah, it sounds like it.
But Microsoft's not alone in this pursuit.
Oh, okay.
So there are other research teams all over the world that are investigating Majorana fermions and their potential.
It's like a quantum gold rush.
Yeah, I like that.
Everyone's rushing to stake their claim on this uncharted territory.
Exactly. And just like in any gold rush, there are going to be setbacks, dead ends, fierce competition.
Yeah, for sure.
Yeah.
Even if Microsoft can overcome all these technical hurdles.
Right.
What about the practical challenges of building this million-qubit computer?
Yeah, you're right. The engineering challenges are immense.
Yeah, it sounds really complex.
They're talking about fabricating a material atom by atom.
Wow.
Creating structures with, nanometer scale precision.
That's crazy.
That's not just a technological hurdle.
Yeah.
It's a manufacturing revolution.
Yeah, that's a great way to put it.
Yeah.
Then there's also the question of software. Do we even have the algorithms and the programming languages?
Yeah, that's another crucial piece.
To use this computer?
Yeah, quantum programming is a very, very nascent field.
Okay.
We're still developing the tools and techniques needed to write software to fully exploit these machines.
It sounds like we're not just talking about a new type of computer.
No.
We're talking about a whole new way of thinking about computation.
Exactly. It's a paradigm shift.
Wow.
It's going to require a new generation of programmers and scientists who are fluent in the language of quantum information.
So even if Microsoft builds this incredible machine, it's just the first step.
Yeah, exactly.
There's a whole ecosystem that needs to be built around it.
For sure.
The software, the applications, the human expertise.
It's a massive undertaking.
Wow.
And it's going to require collaboration.
Okay.
Across disciplines and industries.
Speaking of collaboration, what about the role of government?
Oh, yeah, that's a good point.
We've seen how government funding has driven innovation in other fields.
For sure. So government investment in quantum research is crucial.
Right.
Not just for scientific advancement, but for national security and economic competitiveness.
So we're already seeing this happen.
Oh, yeah, we're seeing countries like the U.S., China, the EU, pouring billions of dollars into quantum initiatives.
Wow, so it really is like a global quantum race.
Yeah, it's kind of got that, feeling of urgency and competition to it.
Okay.
But there's also this growing recognition that we need international cooperation.
Okay, that's good.
You know, quantum technology has the potential to solve global challenges.
Right.
Like climate change and disease.
Yeah, huge things.
But only if we work together.
So it's not just about competition, it's also a collaboration.
Yeah.
And shared responsibility.
Absolutely. We need to make sure that quantum computing is developed and deployed ethically.
Yeah, of course.
With safeguards in place.
Right.
To prevent misuse and ensure that its benefits are shared widely.
So much to consider, so much to discuss.
Yeah, absolutely.
This technology could be incredibly transformative.
Yeah.
But it also comes with a lot of challenges and responsibilities.
For sure.
It's a fascinating time to be alive, right?
Absolutely, it really is.
Witnessing the birth of a technology that could completely reshape the world.
Yeah, it's incredible. It's a good analogy.
Yeah.
Yeah.
So even if Microsoft can overcome all these technical hurdles, what about the practical challenges of actually building this
you're right.
million-qubit computer?
The engineering challenges are immense.
Yeah, it sounds incredibly complex.
They're talking about fabricating a material atom by atom.
Wow.
Creating structures with, nanometer scale precision.
It's crazy.
That's not just a technological hurdle.
Right.
It's a manufacturing revolution.
Yeah, it's a great way to put it.
Yeah.
Then there's also the question of software.
Right.
Do we even have the algorithms?
Right.
And the programming languages?
Yeah, that's another crucial piece.
To even be able to use this computer.
Yeah, quantum programming is a very, very nascent field.
Okay.
We're still developing the tools and techniques needed to write software to fully exploit these machines.
It sounds like we're not just talking about a new type of computer.
No.
We're talking about a whole new way of thinking about computation.
Exactly. It's a paradigm shift.
Wow.
It's going to require a new generation of programmers and scientists who are fluent in the language of quantum information.
So even if Microsoft builds this incredible machine, it's just the first step.
Yeah, exactly.
There's a whole ecosystem that needs to be built around it.
For sure.
The software, the applications, the human expertise.
It's a massive undertaking.
Wow.
And it's going to require collaboration across disciplines and industries.
Speaking of collaboration, what about the role of government in all this?
Oh, yeah. That's a good point.
We've seen how government funding has really driven innovation in other fields.
For sure. So government investment in quantum research is crucial.
Right.
Not just for scientific advancement, but for national security and economic competitiveness.
So we're already seeing this happen.
Oh, yeah. We're seeing countries like the U.S., China, the EU, pouring billions of dollars into quantum initiatives.
Wow, so it really is like a global quantum race.
Yeah, it's kind of got that feeling of urgency and competition to it.
Okay.
But there's also this growing recognition that we need international cooperation.
Okay, that's good.
You know, quantum technology has the potential to solve global challenges.
Right.
Like climate change and disease.
Yeah, huge things.
But only if we work together.
So it's not just about competition.
No.
It's also about collaboration. And shared responsibility.
Absolutely. We need to make sure that quantum computing is developed and deployed ethically.
Yeah, of course.
With safeguards in place to prevent misuse and ensure that its benefits are shared widely.
So much to consider, so much to discuss.
Yeah, absolutely.
This technology could be incredibly transformative.
Yeah.
But it also comes with a lot of challenges and responsibilities.
For sure.
It's a fascinating time to be alive, right?
Absolutely, it really is.
Witnessing the birth of a technology that could completely reshape the world.
Yeah, it's incredible.
So I know Microsoft isn't the only company working on quantum computing.
Oh, absolutely not.
What other approaches are out there?
Well, one of the most prominent is the approach favored by, Google and IBM.
Okay.
Superconducting qubits.
Oh, superconducting qubits, yeah. I remember reading about Google's Willow chip.
Right.
With 105 qubits.
Yep.
That's impressive, but obviously way less than what Microsoft is aiming for.
True, but like we were saying earlier, number of qubits is only part of the story.
Right.
Each approach has its own advantages and disadvantages.
So how do these superconducting qubits actually work?
Well, they rely on the principles of superconductivity, which is this phenomenon where certain materials lose all electrical resistance at extremely low temperatures.
So they basically create these tiny circuits that are super cooled.
Exactly.
So there's zero resistance.
Exactly.
But keeping them at those temperatures sounds like a nightmare.
It definitely presents some engineering challenges.
Yeah, I can imagine.
Building and maintaining these systems.
Yeah.
It's complex and expensive.
Right.
Which is one of the reasons why quantum computers are still pretty rare.
Yeah, that makes sense.
And inaccessible.
So how does this approach compare to Microsoft's in terms of, stability and reliability?
Well, so the theory is that topological qubits offer greater stability because of how the quantum information is encoded in the topology of the material.
So they're less susceptible to those vibrations?
Yeah, potentially.
Changeably.
Yeah. But it's important to remember that both approaches
are
still in the early stages.
Okay.
And there are lots of hurdles to overcome.
It's like we're watching two different teams try to build a skyscraper.
I like that.
Each using different techniques.
Yeah.
And it's just too early to tell who's going to win.
Exactly. And there are even more teams in this race.
Oh, really?
Yeah. Like who?
So there's trapped ion qubits.
Trapped ion qubits, okay.
Which use ions, or charged atoms, that are trapped and manipulated with lasers.
Oh, wow. I did read that trapped ion qubits are very accurate.
Yeah, they've demonstrated some impressive accuracy.
And they can hold their quantum state for a while.
Right, but the big question is scalability.
Oh, okay.
Can they compete with the millions of qubits that, Microsoft and Google are aiming for? Right, so it's a waiting game.
Yeah.
But it's a game with, incredibly high stakes.
For sure, the potential rewards are massive.
Yeah.
It's hard to ignore.
When will we see this become a reality?
Yeah, well, Microsoft thinks they can achieve commercial viability within years, not decades.
But I've also heard experts say that it could be more like 20 years.
Yeah, there's a wide range of opinions.
Okay.
And it really just depends on how quickly we can overcome these technical and engineering challenges.
So we just have to wait to see.
Exactly. Quantum computing has this potential
to
really reshape our world in ways we can barely imagine.
It's true.
But like with any powerful technology,
of course,
we need to approach it responsibly.
Yeah.
Make sure its development and deployment are guided by ethical considerations.
That's a really good point.
Yeah.
It's not something that just happens to us.
No.
It's something that we'll create.
Right. The choices we make today determine what that quantum future will look like.
Well said.
Thank you.
This has been such an amazing deep dive.
Oh, it's been a pleasure.
I really appreciate you walking us through
Of course.
this crazy world of quantum computing.
My pleasure.
I feel like we've only just scratched the surface.
Yeah, there's so much more to explore.
And to everyone listening, keep exploring this topic.
Yeah, read articles, watch videos, ask questions.
Yeah.
Engage in the conversation.
It's a conversation we all need to be the part of.
Exactly.
Who knows, maybe one of you listening will make the next big breakthrough.
That would be amazing.
Until next time, keep those quantum brains buzzing.
Thanks for listening, everyone.